All right, so this is the Margrets Machine, or more specifically, Margaret Atwood, just kind of a play on Margaret Atwood, you know, the one who wrote Handmaid's Tale. Anyway, first of all, read the question. Two blocks are connected by a string of negligible mass, so it holds them together. It makes them a system, but it doesn't really count for anything except making them a system. That passes over massless pulleys that turn with negligible friction. So it's pretty much like those aren't there. Like the string's not getting tangled or stuck or having to move a really heavy weight as it turns. And this is shown in the figure above. The mass M2 of block 2 is greater than the mass of block 1. The blocks are released from rest. So just some things we know about this. Okay, your initial velocity of the system, that's supposed to be an S, is 0 because it starts from rest. Okay, M2 is greater than M1. Okay, so that means that your system's probably going to accelerate this way. That's your acceleration. That means block 1's going to go up. Now, with Atwood machines, you know they deal with Newton's second law, so you know you're probably going to use net force equals mass times acceleration somewhere in here, and have to zoom in and zoom out just to kind of analyze it. And the two forces, since everything's pretty much frictionless, hopefully you know will be some sort of weight, which is probably the weight of 1 and the weight of 2. And then there is a string, so you're going to have a force of tension somewhere in here. So again, I'm not writing these under A or anything. These are just my notes. I can always circle them and draw arrows to wherever they need to be if I decide to use them, but I don't have to. Just, you know, I'm keeping this over here as scratch work so the grader knows that I am not wanting them to grade this. This is just my thoughts. Okay, so now I'm going to look at part A. The dots below are represented by the two blocks. Now remember, this is like the official, like, sacred AP dot to draw your free body diagram on. And free body diagrams, of course, only have forces. And the tails of the arrows come out of the dot, which represents the center of the mass, unless otherwise specified. So anyway, don't put velocity here. Do not put acceleration here. Don't put components here. Don't draw a picture here. Right. The dots below represent the blocks. Draw free body diagrams showing and labeling the forces, not components, exerted on the blocks. Draw the relative lengths of all vectors to the relative magnitudes of all the forces. Basically, the length of the arrow needs to represent, like, for instance, let's look at this. You can see that the weight of block 2 is going to be more than the weight of block 1. That means the arrow representing the weight of block 2 needs to be longer than the arrow that represents the weight of block 1. Okay, so this would be a good example of an arrow that would represent the weight of block 2. So notice what I did here. I put M subscript 2 G. That's important because I am going to have two weights on here, the weight of 1 and the weight of 2. So that subscript goes on the M because the gravitational field doesn't change because they're both presumably on Earth. Okay, notice what I did here. This is for the other one. This is much smaller because the whole system is accelerating down. Like block 2 accelerates towards the ground, and that's going to pull block 1 up. And remember, on Atwood machines, assume everything stops at the pulley unless otherwise stated. So you don't have to worry about this going flying off unless they tell you to worry about that. So I'd label that again. I put my subscript of mass 1 and then the gravitational field. Now the other arrows, this is going to represent the force of tension. See how that's definitely greater than this weight 1? So if you were just looking at this by itself on block 1, you could clearly see that it accelerates upwards. And I've labeled it F subscript capital T, which is of course force of tension. Super important. This force of tension is the same. Remember, on an Atwood machine with like ideal pulleys and massless pulleys and a massless frictionless string, the force of tension is the same throughout. It's just like if you pull a string between your hands. The force of tension is the same throughout. And I would label it no subscripts because these two are the same force of tension. Okay, and this whole section is worth 2 points. You get 2 points for the correct, or 1 point for the correct weights, to where M2G is larger than M1G, and you get 1 point for the force of tension being the same size and pointed upwards. You lose a point for anything that's not that. if you have anything extra. So if you have velocity, acceleration, or a weird force, yeah, you're going to lose points for that. Okay, so now they want you to derive a magnitude of acceleration for block 2. Express your answers in terms of M1, M2, and G. Now, you cannot have any letters aside from those, little g, of course, being gravitational field, but you don't have to use all those letters. We may or may not. So like I mentioned before, this is definitely a Newton's second law problem. Okay, so I'm going to do my work up here. So I've drawn an arrow because remember, human grades this. And I'm going to do something kind of weird with my free body diagram here. Okay, and that's supposed to be an arrow pointing up, and this is an arrow pointing down. The acceleration of this, both blocks are part of the system. The acceleration of the whole system, the magnitude acceleration of the whole system is the same. So that means as fast as block 2 is accelerating towards the ground, block 1 will be accelerating upwards towards the pulley. Remember, it stops at the pulley at the same same magnitude of acceleration. So if this is 8 meters per second squared falling towards the ground, this is 8 meters per second squared going up towards the pulley. So just the direction's different. So what we're going to do is use Newton's second law. And let me be a little bit more specific about this. Okay, so what that gives you is the net force, the magnitude of the net force of the system. Remember, these two are not absolute value signs. These two lines just mean the magnitude. It means the amount without the direction. So the net force on the system equals the mass of the system times the magnitude of acceleration of the system. So let's rearrange that. Okay, or you could just start off with this equation, but basically I just rearranged it to solve for acceleration. I could have just written, instead of all these subscripts, I could have just written, assume everything's for the system, but I didn't. So let's look at how to analyze this in its own weird way. So I'm going to draw the weird free body diagram. So I took this block, I'm just enlarging it down here. I drew free body diagrams where the yellow one is the force of tension, and the blue one's the weight, and same on this one. I'm going to draw these, and what I'm going to do is just turn this sideways and turn this one sideways. And if you notice, this is not a real frame of reference, of course, but these two forces of tension cancel each other out. So yeah, if you look at this, see how that force of tension just kind of removes that one, and now you've just got this big weird new system thing. And the acceleration, it should be kind of obvious. The acceleration for this new kind of fake system thing here is to the right. Or, yeah. And basically what you would want to do is look. The force of tension totally cancels itself out because it's the same for both blocks. It's like the string is just like what's holding them together. So what you want to do is look at what force is going the same way as acceleration and which is going in the opposite way. Okay, so, and that will give you your net force, because remember, net force is just mass times acceleration, and also the force that's going the same way, going parallel to acceleration, and then going the opposite way, or sometimes called anti-parallel for like nerdy people like me. So let's plug this in. Okay, so what I have here is the acceleration of the system, and so first let's put the net force up here, and that, if you look at it, the big force, weight of 2, m subscript 2g, the weight of 1, mass subscript 1, g. So that would be big weight minus little weight. Okay, so then you're going to want to do the mass of the system. So that would be, mass 1 plus mass 2. And I personally, and since it's just the masses, like to put it in parentheses, but that is your choice. And this is your answer. That's it. You're going to probably want to box this in, but It's up to you. So yeah, you want to box that. That's your answer. You don't have to factor out the g here. You can just leave it. In physics, it can be messy. Oh, the only other thing I would add to this is, whoops. That's weird. Okay. I'd probably put the magnitude signs on it, which the computer is not letting me do. Okay, I found a workaround. Yeah, I'd probably put the magnitude signs, but if you forget them, since that's what they ask for, it's probably not the end of the world. So it's just if they ask for a vector, you need to make sure you include a direction. Okay, so let's finish this up. Oh, really quickly, this second part is worth 3 points. You get 1 point for a mention of Newton's second law. So really, I didn't even have to put this top one in here. It could have been the second one as well. I mean, I could have just started with acceleration. You get 1 point for recognizing that the net force is big minus little. So that's m2g, weight 2 minus weight 1, and you get 1 point for putting in the mass correctly, which would be mass 1 plus mass 2, the mass of the system. All right, so this next part. All right, so first of all, this is like a block of mass m3 is added to the system as shown below. There's no friction, so it's still frictionless. You just have this new mass 3. So the system's still gonna accelerate. Well, here, let's see what it says. Indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as the original 2-block system. Explain how you arrived at your answer. All right, so first of all, we're still assuming then that it's accelerating downward, like block 2 is going to drop and block 1 is going to go up. That means block 3 is probably going to go to the right. Again, on Atwood machines, assume everything stops at the pulleys. Nothing jumps the pulley, nothing goes flying unless you're told otherwise, which in algebra-based physics, you should not be told otherwise, but you never know. So first things first, I'm referencing part B because I want to use stuff from over here. I could have drawn arrows, but frankly, that's hard when you're drawing with a mouse on PowerPoint. But if you want to draw an arrow or say, see part B or whatever, that is totally fine. Oops. Okay, so this is what I got from there. I just took the acceleration of the system, magnitude of acceleration of the system equation from right here, and therefore the acceleration of the system, this is alpha. It looks kind of funky, but that's inversely proportional to the mass of the system. Okay, I circled that part just to keep it organized. All right, so the original system, I stated what the mass of the system was, m1 plus m2. Circle that to keep it organized. Then the new system, mass 1 plus mass 2 plus mass 3. Again, I circled it. Then I drew a huge thing, like your alligator thing, to indicate that the original system has less mass. Now, this is the most important part. This looks great. Yay, I've got most of the points. I did not answer this question. It asked me a question about the magnitude of acceleration. I didn't write magnitude, but I put I guess I should put that. The magnitude of the acceleration, you can see it. The magnitude of the acceleration of the new system is greater than the original system. I've saved that up there. The mass, this is because, and by the way, it is totally fine to use therefore and because. That's like using plus and minus. They'll know what it is. Because the mass is greater in the new system. And I've already stated this up here. This is actually pretty close to a paragraph length response where you ask to do that too. Unless they tell you not to use equations, then you can use them. And you can always use like proportionalities, like what I wrote here. That's always okay. All right, so this one is worth, let's see, the first one was worth 2 points, this is worth 3 points, this is worth 2 points. Basically, for saying that the acceleration is greater, and you have to have both, indicating it's because the mass is greater and that's inversely. Oh, I messed that up. Now, let's see if you caught this. Since these are inversely proportional and you've got a greater mass, I should have put less than. This will be good to see who actually watched the video. The magnitude of acceleration of the new system is less. That's because the mass of the new system, that's because the mass is greater in the new system and acceleration and mass are inversely proportional. Always go back and reread your answers. I wouldn't have caught that. I would have just left it. So yeah, be careful about that. So anyway, This one is worth 2 points. You got to have the right answer and back it up. So I wouldn't have gotten any points for that because I had a typo there. But yeah, it's less because they are inversely proportional.